Geospatial question answering, or GeoQA, aims to answer questions about geographic locations using natural language. Traditional GeoQA systems rely on geographic information retrieval techniques, which retrieve stored answers but lack the ability to infer new information. Large language models have also been used but are not reliable for spatial reasoning tasks. This paper explores how probabilistic and conventional qualitative spatial reasoning can enhance GeoQA systems by inferring answers from stored information. Conventional qualitative spatial reasoning uses logical conclusions to form a set of possible spatial relations without distinguishing between more or less probable configurations. Probabilistic qualitative spatial reasoning, on the other hand, estimates the likelihood of different spatial configurations, providing more detailed information, but with occasional errors. The paper compares these two approaches through experiments using real data and synthetic questions. The first experiment involved answering questions about direction relations between places in Melbourne, Australia. We generated a synthetic question corpus and used both conventional and probabilistic reasoners to infer answers to three key question types. What is the spatial relation between two features, termed finding relation queries? Which features relate to one another by a particular spatial relation, termed finding features queries? Whether two features are in a particular spatial relation with each other, termed yes-no queries. We used the two reasoning engines to answer these questions. The conventional reasoner provided a set of possible answers without saying which one was more likely. The probabilistic reasoner, on the other hand, estimated the likelihood of different answers, giving more detailed information. We generated 1,000 different configurations of places and used both reasoning engines to answer the questions. The results showed that the probabilistic reasoner gave more accurate and detailed answers most of the time, but it sometimes made mistakes. The conventional reasoner was always accurate, but often gave less informative answers. For example, looking at finding relation questions, over 70% of generated answers in the probabilistic reasoner were accurate, gave a single, correct, most probable answer. Only about 20% of answers are similarly accurate using the conventional reasoner, with the majority of conventional reasoning outputs either approximate, meaning the correct answer is one of several equally likely possibilities, or uninformative, meaning the universal set of relations was returned as the answer. However, as a result, the probabilistic reasoner also returned almost 30% incorrect answers, where the single most probable answer did not match the ground truth. While this may appear a poor result at first sight, as we explore further in the paper, the majority of incorrect answers also tend to be systematically low probability answers. For example, more than 75% of incorrect finding relation answers were associated with their probability of less than 0.5 using probabilistic reasoning. The second experiment focused on topological relations between geographic footprints in the UK. We started with a dataset of over 3,000 polygonal footprints representing various places in the UK. These footprints were derived from crowdsourced data and the UK Ordnance Survey Gazetteer. Our goal was to see how well the two reasoning methods could answer questions about the spatial relationships between these footprints. We generated questions that required reasoning about these topological relations. For example, we asked questions such as, which footprints are disjoint from a certain point? And is footprint 222072 disjoint from another point? We used the two reasoning engines to answer these questions. The results again showed that the probabilistic reasoner provided more accurate and detailed answers most of the time, but at the cost of lower accuracy. The study demonstrates that probabilistic qualitative spatial reasoning can enhance GeoQA systems by providing more detailed and accurate answers, though at the cost of occasional errors. Conventional qualitative spatial reasoning remains reliable but systematically less informative. In the context of the rising popularity of deep learning techniques, such as large language models and their remarkable capacity to handle and emulate human natural language, knowledge-based AI techniques, such as spatial reasoning, have fallen out of favor in recent years. Nevertheless, we argue in this paper that knowledge-based techniques remain fundamental to geographic information sciences. Large language models remain poorly suited to handling even simplified spatial reasoning, analysis, and logical tasks. Hence, it is the integration of these techniques that holds the future promise for developing advanced GeoQA systems capable of answering complex spatial questions.